In this lesson, we're going to talk about momentum. Momentum is a quantity of motion. And really the best definition for momentum is the mathematical definition for momentum. It is the mass of an object times its velocity. Now remember, velocity is a vector. That means it has a direction. Mass is a scalar. It doesn't have a direction. And the product of a vector and a scalar is a vector, which means momentum is a vector. And that means that direction is important. The direction that the object is moving matters. And so the easiest way to illustrate that is to consider two things that might at first appear to have the same momentum. So here we have a cart that has a mass of, say, 2 kilograms, and a second cart that also has a mass of 2 kilograms. Now, if they're both at rest, neither one of them has any momentum at all. But if they're both moving, they both have momentum. Now, let's say this one is moving to the left. It has a velocity of -4 meters per second. And this one is moving to the right. It has a velocity of +4 meters per second. Then those two carts have equal but opposite momentums, right? This one has a momentum of 4 times 2, which equals 8 kilogram meters per second. Now that is the unit of momentum. It doesn't have a special fancy term like a Newton does. Like kilogram meter per second is in Newton. There is no term for momentum. It's just kilogram meters per second. This one is -4 times 2, which is -8 meters per second. Sorry, kilogram meters per second. Okay, those two momentums are equal and opposite, and we can add them up. We could say that this momentum plus that momentum, the sum of those two momenta, is equal to 0. Now, Newton actually did his work in terms of momentum. It wasn't net force equals mass times acceleration. He was rather interested in how the force acting on an object changed its momentum. And we should look at that. So remember, from Newton's second law, we have that net force equals mass times acceleration. But the definition of acceleration is the rate of change of velocity, so change in velocity divided by time, which means if we plug that into this equation, net force equals mass times change in velocity divided by time, what we really see is this is equal to change in momentum divided by time, right? Mass times velocity is momentum, so mass times change in velocity is change in momentum divided by time. Now, what's neat about this equation is that it applies to not only a non-constant velocity or a changing velocity, but it also works if the mass changes. So this is a little bit more general than Newton's second law on mass and acceleration, because this is just the rate of change of velocity, but we're assuming mass stays the same. In this, mass or velocity or both could change. So let's look at an example problem where we want to find the force, and we're going to use change in momentum to do that. So consider washing a car, and say the hose can spray out 1.5 kilograms of water each second. And it's moving with a velocity of, say, 20 meters per second. I want to know how much force does that water put on the car if, when the water hits the car, it stops. Like it just runs down the side and doesn't splash back. Okay? Well, what we can do is we can say we know its initial velocity, 20 meters per second, and we know its final velocity is 0 meters per second. So I have a V naught of 20, I have a final velocity of 0, but I don't really have a time. However, I also don't really have a mass. So let's pick a time. Let's say that I have a time of 2 seconds. So in 2 seconds, I can see that 3 kilograms of water will be delivered. So our mass is 3 kilograms. Now from that, I can use Newton's second law for momentum. Net force equals change in momentum divided by time. Now the final momentum is equal to 0. This is the momentum of the water. The initial momentum is 1.5 times 2, so that's 3 kilograms, times its velocity, 20. So 3 times 20 divided by the time. Now the amount of time it took for those 3 kilograms to get there was 2 seconds. So there we have our, that's an S for seconds, our change in momentum, which equals -60 divided by 2, which is -30 kilogram meters per second. That is negative 30 newtons. Now, another question to investigate this further would be, what happens if the water actually splashes back? What if it comes back off of the car with a velocity of, say, negative 2 meters per second? How would that change our problem? Well, that would affect us right here, right? Our change in velocity would no longer be 0. Our change in velocity, or our final velocity would no longer be 0, it would be negative 2. And so we'd have to take negative 2 times our 3 kilograms of water minus our 3 kilograms of water times its initial velocity of 20 meters per second, divide that by 2 seconds, and what we would see is that this is actually a greater change in momentum. So negative 6 minus, that is negative 66 divided by 2, which is negative 33 newtons. So there's a force of negative 33 newtons exerted on the water by the car in this case, and a force of only negative 30 newtons exerted on the car in that case. And so what we see is that when something bounces off, that is, comes back with a different velocity, it actually has a greater change in momentum than just stopping.